Welcome back to the Deep Dive. Today we're getting into some really interesting machine learning research that has pretty direct implications for healthcare.
Absolutely. It's an area where, privacy and collaboration are constantly bumping heads.
Exactly. And if you're trying to stay current, especially where ML meets real-world challenges like medical data, this is one to pay attention to.
Right. We're looking at a paper called D-FL-MoE, Decentralized Federated Learning via Mixture of Experts for Medical Data Analysis.
Quite a mouthful. But the core idea seems to tackle a known bottleneck in using federated learning for medicine, doesn't it?
It really does. Federated learning itself is, it's already a big step for privacy, letting different places train models together without pooling sensitive data.
Right. The standard approach is everyone trains locally, then sends updates to a central server, which combines everything.
But that's where the problems start, especially in medicine. This paper points out some key weaknesses there.
Okay, so let's break that down. What's the main issue D-FL-MoE is trying to fix? Why should listeners care about this specific approach? Well, there are two main things, really. First, think about combining AI models trained at, say, a specialist cancer center and a general pediatric clinic.
Very different data, very different expertise.
Exactly. So when that central server just averages their models together, you can actually lose the valuable specific knowledge each one developed. The paper calls this knowledge damage.
Ah, okay. The average model isn't necessarily better for either of them. It gets kind of diluted.
Precisely. You lose that specialized edge. And the second big problem is, it's that central server itself.
The single point of failure.
Right. If that server goes offline, or if connections are patchy, which happens, the whole collaboration just stops. Not ideal when you're dealing with potentially critical medical AI development.
Makes sense. So dependence and dilution. How does D-FL-MoE tackle these? What's the new mechanism?
So the really clever bit is that they ditched the central server for aggregation. It's decentralized.
Okay, so peer-to-peer. Kind of, yeah. Clients think hospitals or clinics directly exchange parts of their models with each other, but not the whole model. They shared just the lightweight head models.
Head models. Explain that a bit.
Think of the main AI model having a body that learns general patterns from, say, medical images, and a head that's trained for a specific task, like spotting a certain type of anomaly.
Gotcha. So they shared just the task-specific part.
Exactly. These heads are much smaller, lighter, easier to share, and crucially, sharing these directly avoids that central averaging step that causes the knowledge damage.
Okay, that addresses the dilution. So they share these heads. Then what? How does a hospital use the heads it receives from others?
Right. This is the other key part. The mixture of experts, or MoE. Each client, each hospital, uses its own MoE approach.
Extra experts.
Okay. It treats its own trained head model as one expert, and all the head models it received from peers as other experts.
Ah, like having a panel of specialists.
Precisely. And then, crucially, each client learns how to combine the predictions from this panel of experts in a way that's best suited for its own local data. It's not just a simple average.
So it's personalized aggregation. Client A might learn to trust expert B more for certain types of cases, based on its own patient data.
That's the core idea. It adaptively weighs the expertise. This client-specific fusion minimizes the knowledge damage and tailors the combined insight.
And because it's decentralized, sharing directly, it solves the single point of failure problem too.
Exactly. Much more robust to network issues, or if one participant drops out temporarily.
Okay, this sounds promising conceptually, but did they, show it works in practice?
Yeah.
With real medical data?
Oh, yeah. The experimental validation is pretty extensive. They used 5 different medical tasks.
5? Like what?
Let's see. Medical image classification, specifically breast cancer histology images at different resolutions. Then medical image super resolution, making low-res images clearer. Also, medical time series classification using sleep data.
Okay. Diverse data types.
Right. And also image classification with different label distributions across clients, and medical image segmentation, finding polyps in scans from different medical centers. So really varied challenges.
And they tested scenarios where the clients have the same type of AI model and where they had different ones.
Yes, both model homogeneity and heterogeneity, which is important because in the real world, different hospitals won't all be using the exact same tech.
True. So what was the bottom line from these experiments?
The bottom line was that D-FL-MoE consistently outperformed the other methods they compared against both standard centralized approaches and other existing decentralized ones.
Across all 5 tasks?
Pretty much, yeah. They showed improvements in accuracy, F1 score, image quality metrics like PSNR and SSIM, and segmentation accuracy using the DICE score. It held up well across the board.
That's pretty compelling evidence. Okay, I think we've got the gist. Maybe we can dig a bit deeper into the paper's structure now, how they lay out their argument.
Sure. So the introduction section basically sets the stage, like we discussed. Highlights federated learning for medical privacy, points out the flaws in centralized systems that knowledge damage and server dependency. Then it introduces D-FL-MoE as the solution.
Standard intro. What about the context? Where does this fit in the history of federated learning?
That's covered in the related works. They give a good overview, tracing from early distributed learning to federated learning. They discuss different centralized FL flavors, aggregating model parameters, or aggregating predictions, or using messenger models.
And they point out the downsides of each centralized version.
Yep, reiterating the knowledge damage potential, sometimes reliance on identical models, and always that central server bottleneck.
Okay.
Then they look at other decentralized efforts. They note that a lot of prior work focused heavily on using blockchain for security and trust.
Right, which is important.
But maybe didn't fully tackle the algorithmic challenges of dealing with diverse data and systems, what they call statistical and system heterogeneity.
So D-FL-MoE positions itself as tackling that specific problem more directly.
Exactly. They frame it as using localized knowledge fusion, that adaptive client-specific MoE, to really minimize the knowledge damage based on each client's needs.
Okay, let's get into the weeds a bit with the method section. How does this localized fusion actually work step by step in D-FL-MoE?
Right. They break it down into three main stages. First is local network training. Each client trains its own model, the body and the head, on its own private data.
Standard local training.
Mostly, but here's a detail. The MoE-related parts of the model are frozen at this stage. The loss function encourages the local model's output to align with what the eventual MoE output will be, sort of pre-tuning it.
Okay, building its own initial expertise. Then comes the sharing.
Stage 2. Localized knowledge exchange. This is where they share only those lightweight head models directly with peers. Not the body, not the whole thing.
Which cuts down communication costs massively, right?
Hugely. They emphasize that. It's a big practical win for decentralized systems where peer-to-peer communication can get heavy.
Makes sense. Less data flying around. And the final stage is putting it all together.
Stage 3. Mixture of experts decision. This is where the magic happens locally. Each client trains its own attention-based MoE model.
Attention-based, okay.
It has a couple of subcomponents. There's a feature space transform module. Think of it like a translator. Client A might represent features differently than client B. This module tries to put the local data into a space that the expert heads can understand.
Kind of like creating a common language for the experts.
Sort of, yeah. Then there's a cross-attention mechanism. This is the really smart part. It looks at the client's current local data, the query, and the predictions coming from all the expert heads, the keys and values. And based on the local data query, it learns to pay more attention, assign higher weights to the predictions from the most relevant experts for that specific input.
So it dynamically decides who to listen to most for this particular case.
Exactly. It's not a fixed weighting.
Yeah.
And the training here fine-tunes this translator module and these attention weights. The actual expert heads and the local model body are kept frozen during this phase.
Wow. Okay. That's quite intricate, but it sounds very adaptive. It really is like that personalized panel of experts.
It is. And then the experiments section, as we touched on, just demonstrates this whole system working across those 5 different medical tasks and setups.
Detailing the data sets like break-ins and sleep EDF, the specific models used in homogeneous and heterogeneous settings.
Right. And the metrics accuracy, F1, PSNR, SIM, dice score, they lay it all out.
And the results showing D-FL-MoE ahead. You also mentioned robustness tests.
Yes, the connection robustness part. They simulated communication links dropping randomly or entire clients disconnecting during training.
Real-world network chaos.
Pretty much. And D-FL-MoE showed much less performance drop compared to a centralized method they tested against. That resilience is a big selling point for practical deployment.
Definitely addresses that central server weakness head-on.
They also double-checked if just using the lightweight heads as experts was good enough.
Compared to using the whole heavier model.
Yeah. And they found the performance was comparable, but the communication cost was way, way lower using just the heads. Validates that design choice.
Smart trade-off.
And finally, the ablation studies. They basically took D-FL-MoE apart piece by piece, removed the MoE, removed the feature space transform to show that each component was actually contributing positively.
Proving the whole is greater than the sum of its parts, and that their specific combo works.
Exactly. And they even tested like centralized versions of their MoE or just aggregating the head centrally, and those didn't perform as well, underlining the benefit of their decentralized client-specific approach.
Okay, so summarizing the key takeaways again. D-FL-MoE avoids knowledge dilution via client-specific MoE fusion. Lightweight head exchange quits communication. Decentralized means robust. And strong empirical results back it up.
That's a good summary. Definitely pushes the envelope for practical, privacy-preserving, collaborative ML in sensitive areas like healthcare.
All right, let's shift gears to our novel notion segment. Taking this D-FL-MoE concept, where could research go next? Any speculative ideas jump out?
Okay, well, one thing that occurs to me builds directly on that mixture of experts idea. What if the expert selection wasn't just about weighting all available experts, but about dynamically choosing a subset? So, idea one. Dynamic expert selection based on task or patient subgroup.
Interesting. So instead of always listening to all the neighbors, sometimes you only listen to a select few. How would that work?
Imagine a hospital using this system. It gets head models from, say, 10 other hospitals. For a routine checkup image, maybe using all 10 experts is fine. But if it's analyzing data for a very specific, rare pediatric condition,
No?
maybe only 2 of those 10 peers actually have significant relevant expertise or data for that. The system could learn to identify, based on the input data's characteristics or the specific diagnostic task, which subset of expert heads are most likely to be helpful, and potentially ignore the others for that specific prediction.
That makes intuitive sense. Filter out the less relevant voices for specific jobs.
Right. The obvious benefit is more focused predictions, but maybe less obviously, it could actively prevent negative transfer.
Negative transfer.
Yeah, where knowledge from an irrelevant domain or data set actually hurts performance on the target task. If a hospital specializing in, I don't know, sports injuries shares its head model, it might not be helpful and could even be detrimental for diagnosing that rare pediatric condition. Dynamic selection could filter that out.
And maybe it could even tell you which peers are considered experts for different things. Like, oh, for lung scans, we always rely heavily on Hospital X's model.
Exactly. Potential gains in interpretability, too. So the real-world impact could be even more tailored, accurate AI assistance, really leveraging the right distributed knowledge for each case. It connects to attention, but adds a layer of explicit selection.
Cool idea. Got another one.
Yeah, thinking about the decentralized nature and real-world deployment, how do you ensure quality control? So idea 2. Incentive mechanisms for high-quality expert contributions.
So making sure the expert heads being shared are actually any good.
Precisely. In a network with dozens of institutions, some might invest more in training high-quality local models than others. Some might even, theoretically, contribute poor models free writing, or worse.
And how would incentives work here? Pay for performance.
Could be various ways. Maybe a reputation score for each participant's shared heads based on how often they are weighted highly by others' MoE models, or how much they contribute to overall performance gains.
Okay, a quality score.
Or potentially integrating blockchain concepts, which the paper acknowledges are used in some decentralized FL work for transparent tracking of contributions, and maybe even micro-rewards for demonstrably useful expertise.
The obvious benefit is motivating everyone to contribute their best work.
Yes, but maybe less obviously, it could build a more trustworthy ecosystem. If there are mechanisms to verify and reward quality, it discourages low-quality contributions and could make the whole system more reliable and robust against bad actors or just poorly trained models.
It adds a layer of governance and quality assurance to the decentralized setup.
Exactly. Fostering a healthier, more effective collaborative environment.
Both really interesting potential directions. And of course, our usual disclaimer. These are just speculative thoughts, food for thought, not validated research paths.
Absolutely. Purely for discussion and sparking ideas.
Well, this has been fascinating. The D-FL-MoE paper really does seem like a solid step forward for making federated learning work better, especially in the tricky context of medicine.
Agreed. It tackles some fundamental limitations in a smart way.
For everyone listening, we definitely recommend checking out the paper itself. If you want the full technical details, we'll have the link in the description.
Yeah, it's worth the read. And it does make you think about the future of decentralized collaboration, not just in healthcare, but maybe other sensitive fields too.
A great final thought. What does truly robust, private, decentralized intelligence look like? Thanks for joining us on this deep dive.
Thanks for having me.